Deterministic finite automata have a simple path of computation. Given a state and a valid input, we can transition to only one other state at a time. This gives us a direct route through the machine. Non-determinism means that given a valid input or an empty input, we can transition to several states at the same time. Here's an example machine. In a DFA, each state has exactly one exit arrow for each symbol in the machine's alphabet. An NFA can have multiple, like Q1 can stay in Q1, or exit to Q2 when given an input of 1. In an NFA, a state can have 0 or more exit transitions. Another difference is the epsilon symbol. Epsilon represents an empty input, or no input if you prefer to think about it. It can behave something like an automatic transition that doesn't consume another character. So how do we track computation through a machine like this? Let's walk through an example with the above machine. Given an input of 0, we continue in our start state Q1. Then, when given an input of 1, we can think of the machine as copying itself, with one copy remaining in Q1 and the other copy moving to Q2. At this point in Q2, we have an epsilon exit transition, and when we see this, we don't read any input, but we can create another copy of the machine that will follow each epsilon transition. In this case, we create another copy of the machine and move it to state Q3. Next, let's read a 0. Our top machine continues in Q1, our middle machine moves to Q3, and our bottom copy has no valid transition, so it dies and goes away. Now let's read a 1. Our top machine will split again, with one machine staying in Q1 and the other copy going to Q2. Our machine in Q3 transitions into the accept state. At this point, let's say our input is read and complete. Our bottom machine is in the accept state, so we consider the input string to be a part of the machine's language. The top two machines are not in accept state, so we let them fade away. This type of computation lends itself to being thought of as a tree, with each input creating child nodes and dissolving branches as invalid paths are discovered in the machine. This particular NFA will accept strings that contain either 101 or 11 as a substring. These NFAs are very useful, and in the next video we will show that every NFA can be converted into a DFA, and because of this, they both recognize the same set of regular languages. In this regard, one isn't necessarily more powerful than the other, but NFAs allow us to create finite automatas for languages in a much simpler form than their DFA counterparts. Let's look at some examples. Let A be a language that has 1 in the third position from the end of a string. The NFA for this would look like this. The way this machine works is that it will stay in the start state Q1 until one of its branching copies, air quotes, guesses that it is 3 places from the end and it will read the rest of the string. In order to represent this in a DFA, we would have to create something like this. Now take a look at this finite automata. In this case, the machine recognizes a language where the number of zeros in a string is a multiple of 2 or 3. When receiving the first symbol, the machine will travel down both paths simultaneously, and the path that is satisfied by the input will survive, or if the input is not a member of the language, both paths will die. This is a case where the epsilon transition shows its usefulness. Now let's talk about the formal definition of an NFA. They are incredibly similar to the DFA with one exception. The transition function must also include an epsilon transition for each state. This means that if we have states Q1 and Q2 and an alphabet of zeros and ones, we also have to define the epsilon transition like so, even if it means that it does nothing. For an NFA, the definition of computation is also very similar to a DFA. The only change is that when given an input, there exists a state that is a member of any of the multiple branching options. In the next video, we will show how NFAs and DFAs are equivalent and how to convert between them. See you there.